All right, in today's lesson, we're going to look at the third method for solving systems of equations, and this method is called elimination. So we have learned solving systems by the graphing method, which is where we graph both lines and see that point of intersection for our lines, and that point represents the solution. We also looked at substitution method, where we isolate a variable and use that variable's expression in the other equation, solve for the one variable left, and then use that variable to solve for the other. A little harder to explain that one just by words. But then finally, today we're going to look at the elimination method. Now, if you'll remember, the graphing method is more of an estimation, an approximation, because unless your lines go straight through, perfectly through some grid line intersections, it's hard to tell exactly where a point of intersection between your two lines might fall on the grid. So that one's more of an approximation. But substitution is an exact method for solving, and elimination, today's method, will also be a great method for finding exact solutions to systems. You may also hear the elimination method referred to as the combination method, and we'll talk about why in a moment. But essentially, what we do is we can add our two equations together. And when we do this, one of the variables will eliminate, allowing us to solve for the other. If a variable is eliminated, right, it's going away. It goes away. So you'll see if you do this elimination method properly, one of your variables will go away, making it quite simple to solve for the one that's left and remaining there. Okay, so we can add any two equations together because of equality. The addition property of equality allows us to add the same value to both sides of an equation because it states that in doing so, we never actually change the fact that the two sides are equal. If I have a 5 equals 5, and then I decide to add 2 to the left side and then 2 to the right side, this is new what I'm adding, but it's the same value on both sides, so I still have a true statement at the end after I've added both sides of my equation. So this is the idea behind us adding our equations together. And so what this, in this problem, we have x plus y equals 28 and 2x minus y equals 2. And so to add these equations together, if I know that 2x minus y is equal to 2, then I can take the 2x minus y and add it to the left side of the top equation, as long as I take the 2 and add it to the right side of that same top equation, meaning I'm adding the same value to both sides of our equation. So this is how that might look. I bring down the x plus y from the original top equation and add to it the left side of the bottom of equation, 2x minus y. Then I take that 28 from the top equation, I add to it the 2 from the bottom. And here's where we can see that we're combining two equations, hence why we might call this the combination method. From here, we need to simplify and solve and do what we can with our equation to work with it and hopefully find a value for either x or y. So on the left, when you begin to simplify, we've got an x term and a 2x term, which will combine. That will give us a 3x. But what's really interesting here is when we look at combining the plus y, a positive y, minus a y. When I combine those y's, y minus y is 0. Those go away, leaving us with just 3x equals 30. And this is where elimination comes from. When we added our two equations together, one of the variables eliminated itself. So from here to solve for x, I would just divide both sides by 3, giving us x's value to be 10. The beauty of this is once we have x's value to be 10, we can use that 10 back in either of the original equations. So if I'm using x plus y, oh, my board is not letting me write cleanly, equals 28. And then I could replace the x with a 10, making it look all spooky. 10 plus y equals 28. Anyways, and then we solve for y. Subtract 10 from both sides to get y to be 18. Remember that this x and y comes together to make a point 10 comma 18, and this would be the point that these two original lines would intersect at in the grid. So the value of x is 10 and the value of y is 18. All right, so that method there can get a little bit lengthy. If you look at this step here, you can see how we had 4 terms there. Here we only had 2, but you can imagine it could be even longer. And you more commonly have learned to add vertically. If you think about when you were in lower grades, maybe adding something like 12 and 13, you would not set it up like that. You would typically set it up vertically and stack them, right? So using this, we can do this with equations as well. And here is the more common way that you're going to see elimination set up for you or solved is by stacking our equations vertically. So this is a shorthand way to do this, and when you stack your equations vertically, there are a couple things that are incredibly important. The first is that you make sure that the same kinds of terms are stacked on top of each other. So notice I have all x terms in the first column here. Then I have all y's, and then I have all numbers by themselves. What's also very important is that your equal signs are in the same place in both equations. So, for example, if you were to have had this here like this would not be legal because your equal signs are not in the same place. So if ever your equations don't have their equal signs in the same place, you may need to do some rearranging first before you go ahead and stack them. Okay, from here you can add vertically just as you would adding any 2 or 3 digit numbers that you stacked vertically. So I would look with my x's first. X plus 2x gives us a 3x, and then adding vertically the y minus the y, it goes away, and then 28 plus the 2 is 30. So I wrote 0y here, but hopefully you know that that would go away. What's important is also that you indicate that we are adding these equations so that visually you have that as your reminder that we're adding each of these columns. Again, leaving us with 3x equals 30, divide both sides by 3, x equals 10, and then you use the x equals 10 back in an original equation, solve for the y to be 18. So this is how we're going to be setting them up today, is stacking vertically. So I want to push this a little bit further. That last example was very convenient because when we added the equations, one of the set of variables conveniently eliminated itself without us really having to do anything. And as wonderful it would be if that could always happen, it will not always be that simple that just adding 2 random equations together, one of the variables would go away. So here's an example where if I were to add right away here, they're stacked vertically for me. I can see x's, y's, and equal signs are all in the same place, so I could just go and add vertically. But if I do that, I'm left with a 5x, a negative y plus 4y is a plus 3y, and 6 plus negative 2 is 4. Well, when we did that, we're still left with 2 variables. So this isn't actually helpful to us, adding our 2 equations, because one of the variables didn't eliminate. So that brings us to what might we be able to do to our equations so that when we add them, one of the variables might eliminate. So when this happens, you can multiply through by one or both equations until you have one of the variables as opposites so that they will cancel out. So not only can we use the addition property of equality, we can use the multiplication property of equality to help us out here to solve a system of equations. So remember that multiplying both sides by the same exact number again holds the equality. It keeps both sides equal, so it's a totally legal math move to make. So if you're looking at your first equation up here, you may choose to multiply the whole thing through by maybe 4. The The reason that I chose 4 is because I'm looking ahead at this equation here. And my x has a 3 in front of it, and the top x in the blue equation has a 2 in front of it. My y in the bottom equation has a 4, and this y up here just has a 1 as its coefficient, so it's pretty easy to make that y a 4y by multiplying it by 4. But remember, I can't just multiply that y by 4. I need to multiply all of the terms in this top equation by 4. So that would turn it into an 8x minus 4y equals 24. And I didn't multiply the bottom equation through by anything, so I would just bring it down as it's given. Notice that now that we've done this, our y's all have opposite signs. So one's negative and one's positive, and they both have a 4 in front of them. So that means if I go and add my two equations together, then when I add those y's, they will eliminate. So I'll be left with 8 plus 3x is 11x. Negative 4y plus 4y is 0 and goes away. And 24 plus a negative 2 is 22. Now to solve, divide by 11, and x's value is equal to 2. I believe I carried on to the next slide for space. Yes, okay, so we just found on this last slide that x's value was 2, so I'm just going to finish my work here. Once we find x's value to be 2, you can use either of the original equations to help you solve for the y. So this one looks pretty straightforward and simple. So instead of 2x, now we know x's value is 2 minus y equals 6. You do not need to use the equation you multiplied through by. You can use the very original one. So 2 times 2 is 4 minus y equals 6. Subtract 4 from both sides. So negative y, that is a y, equals 2. Divide by negative 1, and y equals negative 2. And the solution to this system is the point 2, negative 2. And we're finished. All right. Let's move on to just summarizing the steps for elimination that we just saw. Step 1 is to multiply through your equations to get one set of variables as opposites. Now in the example we just saw, we only had to multiply one equation through. We may have to do both, multiply both equations through by a number. We'll look at some like that today. And sometimes step 1 here is done for you. One of the sets of variables would already eliminate. So you won't have to do this. Once you've done that, though, you will add or subtract your two equations. So if your variables that you want to eliminate have the same sign, then you would go ahead and subtract them. But if they're already opposite signs, then adding them would help you eliminate. So you can make that decision. It's just important to indicate what operation you're doing to your two equations with a big plus or minus sign. You'll solve for the variable that is left. Use the value you got to substitute back into an original equation and solve for the other variable. Then write your solution as an ordered pair, and don't forget to check your values into your equations. Okay, so let's look at this next example. We want to solve this system using the elimination method. However, if we look at the way that the equations are stacked up, neither of our variables would eliminate if we went to go and solve for them right now. Sorry, this is misaligned again. Okay, so if I were to try to add right away, I would not be able to eliminate any of my variables, nor if I tried to subtract. So because of this, we need to multiply one or both equations through by a number. So if I look at my x's right here, there's not really a convenient number that I could multiply just one by. I can't multiply 3 by something to get 5. Surely I could use a fraction But then that would turn the y and the 7 into fractions. So we're going to try to use whole or integer numbers when we multiply through to make that work nice and clean and easy for us. And going backwards, I'd have to actually divide 5 by a fraction to get it to become 3. So that's a lot of work. Let's look at the y's. Hopefully you can see that 2 does go cleanly into 4. So by multiplying the bottom equation through by 2, we will be able to turn that y value into a 4. And I'm actually going to use a positive 2. You may be thinking ahead and seeing multiplying through by a negative 2 would work, but I want to show you a little something real quick. So always start by recopying the equation you're not doing anything to. Take the time to rewrite it down below. Don't try to just cross out this second one and visually use the top and then whatever work you have below. Take the time to recopy. Now 2 times 2y is 4y. 2 times 5x is a positive 10x, and 2 times 10 is 20. So I'm showing you this way using a positive 2 to multiply through because sometimes we're not able or we're not thinking all the way ahead about, oh, these need to eliminate. So if I'm looking here at my 4y and 4y, if I were to add those, that would give me 8y, and that's not getting rid of the y. So we are actually going to want to subtract these two equations. So I'm going to put a big subtraction sign and circle it. And it's just important that you are following that subtraction. So if I start with 4y minus 4y, that's 0y, that goes away. So let's move over. Negative 3x minus 10x is a negative 13x. And 7 minus 20 is negative 13. Now I just solve for that one remaining x by dividing both sides by negative 13, meaning that x's value is equal to 1. We're not quite finished because we need to solve for y. So take one of your original equations, I'll take the second one, and replace the x in it with a 1. And solve. So subtract 5 from both sides, so 2y equals 5. Divide both sides by 2, and y equals 5 halves. Meaning that the solution to this system is the point 1, 5 halves. And that would be the point where these two lines would intersect if we were to graph them. That's the x and y value that makes both equations true. Here's one for you to practice on your own. So take a moment and multiply one or both equations through by a number so that one of your variables will eliminate. And click pause to work this out. When you're ready to check, click play. Okay, so here we are. You may have chosen to multiply the top through by 4. That's worked out on the left. You may have chosen to multiply the top through by 6. That is shown on the right. However you do that, we should all get the solution negative 4/5 for x and 11/5 for y. Okay, here's our next example. We have variables a and b in this problem. That should not change your method in any way, though. So we will solve this as normal. In this problem, though, I'm going to walk us through how to set this one up because we'll see that with our a's, there really isn't a convenient number that I can multiply 7 by to get 9 or vice versa. And same with the b term. So this is a little bit different from what we've seen up to now. So this is a scenario where we may need to multiply, or we will need to multiply both equations through by a number. So I'm going to look for a least common multiple of one of the sets of variables. And I'm even going to look for one that has smaller numbers. So 9 and 7, we know I can multiply those together. They both go into 63. That's quite a large number, though. 2 and 3 both go into 6. So let's use the b's to eliminate. So to get the first equation's b to be a 6, I need to multiply that one through by a 3. And the bottom equation I would need to multiply through by a 2 so that the bottom equation has a 6 coefficient on the b as well. So this step is us working to get the b's to have the same coefficient, the same number in front of them. And I can multiply both equations through by different numbers, just as we're seeing right here. As long as you multiply every term in the equation through by that number you're using, you're maintaining the equality, and this is perfectly fine to do. Oops, so there it is written again. So from there, multiplying through to each one, your new equations that you're using would look like 27a minus 6b equals negative 24, and negative 14a plus 6b equals positive 24. I can now see that my b's have the same coefficient in front of them, and they have opposite signs. So that means that adding these together will help me eliminate the b's. So take it from here, click pause, work it out. When you're ready to check, click play. Okay, so hopefully you have solved and found that a's value would be 0. Use a's value back into one of the original equations, solve for b, and you get it to be 4. Now, we haven't seen one with variables other than x and y in it yet. When you write them as a point, you would just write them in alphabetical order, so a comma b. Or for a problem like this, just leaving it a equals 0 and b equals 4, and not writing it as an ordered pair would be okay for my class. All right, here's your next practice problem. Hopefully you can see pretty quickly that this conveniently has the coefficients the same on the x's and the y's. So let's just solve this one together and talk through it. For this problem, we would need to subtract to be able to eliminate one of the sets of variables. You may also choose to multiply one of the equations through by a negative 1 so that then all you have to do is add them. That choice is up to you. Regardless of what you do, when I subtract these, this board being misaligned is quite annoying. Once I subtract these, the 4x minus 4x eliminates, and the 3y minus 3y eliminates, leaving us with just a 0 on the left and a negative 5 on the right. So here it is here, multiplied through by negative on the bottom equation. Is 0 equal to negative 5? This is interesting. Our variables went away, and we're left with 0 equals negative 5. Hopefully you recognize that that is not true. That makes no sense. 0 is not equal to negative 5. So this is, in fact, a false statement. So what this implies is that these two equations actually don't have a solution to the system. There is no point that these two lines would ever meet at the same place at. And we've seen this in graphing, and this is an example of two parallel lines, meaning they will never intersect, so there is no solution to this system. Okay, here's your next example. I'll have you work to isolate a variable and solve, so click pause. When you're ready to check, click play. Okay, so hopefully you multiplied one equation through by 2, the bottom equation through by 2. That would have probably been the quickest way to get the same coefficients on the y's. And once you do that, you also could have multiplied the top equation through by 1/2, and that would have been fine as well. When we eliminate here, though, whoops, okay, come on. There we go. We get 0 equal to 0. So this time, yes, both variables went away, but we're left with a true statement. And we've seen this before as well. This is actually an example of two lines that are identical, meaning they're laying on top of each other. And that implies infinite solutions. They are the exact same line. And that concludes our elimination lesson. So I hope that you will enjoy practicing with this method and be able to find times where it is more appropriate and easier to use than substitution. All right.